Hello and welcome to the CIBSE West Midlands Region CPD webinar on carbon steel tubes advanced level details. Today's seminar will cover the development of and issues with tube specifications, tube manufacturing and testing, examination of building services corrosion issues, examination of installation and commissioning issues including case studies, and the digital data, the future supply chain challenges. Our speaker this evening is Dr. Chris Owen, who is Customer Technical Services Manager at Tata Steel UK, Building and Industrial Services Tube Products. He's the chair of the BMTFA, the British Metals, Tubes and Fittings Association Technical Committee, and a member of the BSA, Building Engineering Services Association Affiliates Committee and Pipework Working Group. Chris proactively promotes the benefits of carbon steel pipework and product specification awareness within building and industrial services. We thank Chris and all the team behind the scenes at Tata Steel for their help and support in today's event. Just a few housekeeping tasks before we get started, if I may. Please keep your cameras and microphones switched off unless you'd like to ask a question, but bear in mind that this session is being recorded and will be made available on various social media platforms, including YouTube and our podcast, for people to catch up with afterwards. Alternatively, please use the chat function to ask any questions during the presentation. Please contact Chris directly for a copy of the presentation slides after the event, contact details to follow, and please get in touch by emailing cpd@cibsewm.org for CPD certificates, stating your name, the subject of the event and the date, and they'll be emailed to you afterwards. I'd like to take the opportunity to thank you all for joining us for today's session, but also thank Chris for sharing with us today too. I'm really looking forward to hearing it. Chris, over to you.
Okay, thank you. So this is the advanced level. We tend to do a little bit more in-depth sort of review of the various subjects which we've covered previously. What I wanted to try and do is, again, just go into a little bit more detail around the sort of pipework specifications, particularly around the manufacturing types, and also, again, look at corrosion, issues which we've seen in terms of pipework installation, and then obviously look at an example of corrosion and commissioning processes as well. So for those who were on the earlier CPD, the basic CPD, I explained who Tata Steel are. So Tata Steel is a manufacturer of steel. We've been producing products in the UK market for many years, stroke decades. We have a whole range of different products which then go into different market sectors. But as you can see from the image here, for myself in building services is what we call construction fit out market sector activities. When we talk about building services, we're talking about pipework, which is obviously used for the conveyance of water, gas, either as part of the HVAC system or as part of a again, much bigger services within the building. We also obviously see our products being used more and more within industrial applications. And again, I think it's worth pointing out that what we start to see now in terms of pipework specifications is a change in what we call traditional size range in building services. As the tall buildings have obviously got taller and the pipework, particularly the riser, has got bigger, we're starting to see industrial products being pulled in. And that's one of the reasons why we have two brands in the UK market, our Install Plus, which is made at Corby, and our Inline, which is made at Hartlepool. The Corby size range traditionally went up to 6-inch, 150 nominal bore. That was basically to satisfy the old BS 1387, which was the sort of gasless stroke building services product standard. Over the years, we've had that standard replaced with BSEN 10255, but again, it only goes up to 6-inch. And what we've seen now with the larger diameter pipework being pulled in, we're pulling in the sort of industrial specs, which still is referred to as API, it's legacy specification. And this comes about because many decades ago, when larger diameter pipework was wanted, API, American Petroleum Institute pipework, was readily available in the UK market. It was here because of the North Sea and the American investment in that North Sea. So we tend to see people still talking about sort of old legacy, medium weight, heavy weight, red band, blue band, shed 20, shed 40. So it's a bit of a mixed match of different terminologies which are used. The little schematic diagram sort of shows the the sort of relationship which we have. Most of the building structures now with large diameter pipework is the what we call our inline, and then the runoffs being the sort of smaller Corby sizes. In both cases, the steel which we use to make those tubes comes from Port Talbot in Wales. And again, we've got something in the pack about the sort of steel chemistries and why it's important to specify the types of grades and steel which you need in terms of mechanical properties, testing, validation, compliance, and weldability, etc. Okay, so as I mentioned, we have two particular brands in the UK market. And again, what I've tried to highlight here is the fact that a single pipework specification, unfortunately, is not good enough. What we have in terms of the pipework standards are what's called technical delivery conditions. And those technical delivery conditions define everything from how that tube needs to be made, how it needs to be in terms of its dimensions, its tolerances, the testing, anything which is put on that in terms of marking, certification. And one standard doesn't really cover all the requirements correctly. So we tend to make reference to multiple standards, which then gives you a much clearer picture about what it is you want in terms of that tube and what that tube will do. So the 10255 obviously defines the main technical delivery conditions in terms of the wall sizes, the ODs, what end finishes and coating finishes are available. It also gives you the opportunity of CE marking to either fuel, air and gas or water under the construction products regulation. But it doesn't tell you whether that product has been produced by a cold film route, a hot finish route, a seamless route, or welded route. So that's why we refer to the pressure pipe standards as well, the 10217, which shows that it's welded, and the part 2, which shows that it's suitable for elevated temperature use. And then we have the grade of the steel which is used. So in this instance, it's actually a structure pressure grade, which is a 235 minimum yield strength with a GH, which is a quality designation, which defines exactly what sort of additional product testing is carried out alongside the normal standard testing, which then shows its suitability for things like elevated temperature use. So in the case of this product, we are obviously suitable and rated up to 300 degrees C. And of course, with having 10255 under construction products regulation and then 10217, which is harmonized under the PED, Pressure Equipment Directive, it allows people then to tick the box in terms of compliance. One of the advantages of this standard is obviously it's a very restricted OD and wall thicknesses, which is good because it means then that it's readily stocked in the key sizes and fittings are readily available to match. When we get to the larger diameter pipework, again, the API reference in there because the walls tend to be related to the shed 20, shed 40, but you can notice that instead of a 235 grade, we're actually a 265 grade, so a stronger grade of steel. And the reason for this is it allows us to go to thinner walls and still maintain the service life and pressure integrity. But that stronger grade of steel allows you to basically achieve that without adding additional cost, additional mass, and additional CO2. You can see that the 10217 is referenced because, again, the PED, European Pressure Product, and European Pressure Equipment Directive as well. And obviously the ISO 3183 is the equivalent to the API. And as we're a European mill, then obviously all our systems, procedures, quality management systems are all set up alongside the European requirements rather than the American requirements. We can do standalone API, but really, unless you're supplying directly into America, most of the European projects actually do need to have the ISO or the EN version to allow demonstration to full compliance in terms of the PED. And you can see at the bottom there, but again, because this product is used in industrial applications, there's, as well as the PED, there's reference to the German pressure standards as well, because again, we supply a lot of this product into Europe. And very similar to the previous Install Plus setup, again, restricted ODs, restricted wall thicknesses, which is good because then again, it means that good end matching, compliance with fittings, readily available sizes are available on the market. What is interesting is when you look at the 6-inch size here, it's a 168.3, whereas the 6-inch size on the other standard is a 165.1. So we do see sometimes confusion when people are bringing industrial products in that the fittings may not be suitable, may not match, because obviously there's two different ODs across the different specs, which again can cause a little bit of confusion with end users. Now, as I've mentioned, we supply into building services and industrial applications, and that covers a whole range of different temperature and pressure requirements. Again, we've done a lot of work, and I showed this on my previous CPD. A lot of work's been done with the likes of BMTFA and BISA to look at the typical ranges of temperature and pressure. And this is to allow us to then cross-reference with the production standards in terms of the fittings and the pipework to make sure that the right specifications are being used for the right applications. And recently we've seen changes in legislation, particularly around what we call cold form tube, which means that it's no longer suitable under the PD and has always been only technically suitable for temperatures up to 50 degrees C. So fine for chilled water systems, but if you're using it for lower high temperature hot water systems, then technically it's the wrong product to use. And the PED can apply at pressures above 0.5 bar. And I know there's some restrictions in there if you don't go over a certain pipe diameter, but if you connect to something 8-inch, 200 normal bores and above, then the PED actually pulls the smaller diameters in because you take it as a system. So the PED is quite important. And obviously we're seeing a lot more focus on compliance, particularly post-Grenfell, when people obviously want to make sure that they are using the right products in the right applications and checks are being done. Problem we have these days is what we see in terms of the project risks is we're still coming across specifications which are basically cut and paste. So old previous specs which have been copied across into new projects. The pipework specifications may not have been updated, so they're still referring to old legacy standards. We always see missing information when people are specifying pipework. They tend not to actually put the grade or the quality designations in, and that's quite important, and we'll talk about that in a little bit. Or we see conflicting requirements where they ask for a particular product, but that product is only suitable for, say, room temperature, but they're using it on a boiler tube application or high temperature application. So again, you can't use that product. And we do see people not actually referring to any compliance approvals they might need until it's too late. Normally at the end of the process, when someone's looking at signing off the pipe work, you have an insurance company which comes in and they'll want to make sure that the right tube's being used. So they'll ask about the compliance. And that obviously then is a problem if you've not used the right product. And then just building on what I said previously about the legacy specifications, the problem is that they are out of date. They make reference to old ways of making tubes, and we obviously need to get people onto the new standards. The new standards, as you can see, are quite complicated in that they define multiple welding processes for welded tube or a seamless manufacturing process. So again, without clearly defining what you're getting, you could get a mixture of different products in a pipework system, which can cause some issues. So it's very important that you clearly define exactly what it is you're getting. And that's not just for the suitability of that product when it's in an application. It actually goes back to how we make that tube. So what we've got here is a couple of the tables which come out of one of the pressure pipe standards. And you can see it's quite important that the correct grade and material is identified. So instead of just saying carbon steel tube or 10255 tube, you really need to define the sort of the actual grade of steel, because you can see each of those grades of steels have different steel chemistries. And that is basically the different recipes which we have to make the steel to be able to achieve those chemical compositions, which in turn results in the mechanical properties. So you can see how those chemical compositions, if you look down at the table 4, that has the different mechanical properties in terms of the yield and the range of tensiles. They will change as a result of that chemical composition. Okay. So if you're not clearly defining what you want, you might end up with a default condition, which is going to be the lowest chemical composition, the lowest mechanical properties. The thing about table 4 is it also defines the different testing requirements in terms of ductility. So we'll do what's known as a Sharpie impact test, which is the image in the top right hand corner. So we'll take a section of that tube and we'll basically be able to do room temperature and low temperature impacts. So again, depending on what grade you're specifying, they might have different lower impact temperatures. And then obviously we've got tensile tests, which are done again at room temperature and also elevated temperature. So again, in the table 5, which is from the 10217 part 2 standard, you can clearly see that the yield actually changes as that temperature increases. And we have to validate that as a manufacturer to show that we are satisfying those requirements in full. So carbon steel is relatively straightforward in terms of its steel chemistry. However, variations of that chemistry give you the different mechanical properties as a result of the different grades of steel and strengths. That has a knock-on effect in terms of clearly showing what products are suitable for particular applications. And this is where we get into the sort of the quality designations. So you can see where we've got grade information, the minimum yield. We've got the type, which is either a quality designation, either a GT, a GH, PSL1, PSL2. This all then tells us as a manufacturer what we need to do in terms of the steel, the manufacturing tolerances, and the testing which we have to put in place to demonstrate that product is fit for purpose. And again, you can see that within all the standards referenced, there's an option for a welded, there's options for a seamless, and within the welded options, you've got obviously the cold form or the hot finish manufacturing types. And really what I'm going to do now is just go into a little bit more detail about those different manufacturing types. So again, when we talk about welded tube, we're talking about what's known as high frequency induction, HFI, or high frequency welded, HFW. So this is where we basically take a coil of steel, a strip, we form it into a tube profile, and then that tube profile is that seam is welded. And it's not welded by filler material. It's basically an induction process where we superheat the free edges of the strip, squeeze it together. No material is added in there other than when we're looking at what is basically called a submerged arc welded product. Now, we don't manufacture that as Tata, but a company called Liberty make that up at Hartlepool. And this is where the large diameter pipe work is made using plate, and they might form two sections of plate into circles and weld them together. Of course, they'll use filler material there. So when you start using filler materials, then your mechanical properties are going to be a function of that filler weld material which is being used. For the sake of this CPD, we're just talking about sort of coil-based welding where no filler material is used, and the standards clearly define exactly the manufacturing processes, be it a welded traditional thick wall, welded precision thin wall, or a seamless tube. So when we look at welded traditional, this is obviously something which can either be a cold form route or hot finish route. Now, basically the coil comes in, as we've already discussed, that coil can have different steel chemistries to achieve different steel grades, that can have different recycled content, again, depending on what we're doing, from either making virgin steel or different production routes for that coil, which we'll talk about later. And again, the different testing requirements, not just on the tube, but the actual feedstock material. The coil undergoes quite a lot of testing and validation even before it gets into our tube manufacturing process. And you can see from the schematic that we're basically taking that coil, we weld the nose to the tail of the previous coil's continuous process, and we're forming it into a tube profile, which then goes through that high frequency induction welder, and we cause the free ends to superheat, we squeeze it together. So that is basically a cold form tube. What we then do at Tata is we take that cold form tube and we'll put it through either a furnace for full body normalization or weld line annealing, which applies localized heat at that weld seam to remove those stresses and remove what we call the heat affected zone. And the reason why we do that is because the weld seam is an area of weakness. It's an area of stress where the mechanical properties are very different. The heat affected zone is very visible when you take a section of that tube and polish it up. You can clearly see the discoloration. There's a variation in mechanical properties across there, as well as obviously the problems associated with ductility, which then means that if these tubes are work hardened or the weld quality is not good or the steel is not as good as what it should be, then you can see a lot of splitting, tearing of threads, for example, or collapsing of the actual tube itself. What we try to do in the hot finish process is remove all those stresses and eliminate the sort of heat affected zone. And that gives us a tube which can be more readily manipulated without the risk of splitting or collapsing. And the images on the left show examples of where tubes have split along that weld line. And on the right, you can see when we have normalized tubes as part of our own in-house testing and validation process, which is above and beyond what the standard asks for, we'll do drift expansion tests and flattening tests. So basically we take the tube and we try and force it apart, see whether it splits, and we flatten it both on the weld and 90 degrees off the weld to again see if we can initiate splits. Once we know that that weld is meets our requirements, then obviously it can go onto the into the parent hollow and into what we call stretch reduction at Corby. And this allows us then to superheat that master tube and then elongate it to get all the different shapes and profiles we need to service our customer requirements. And we've got lots of work which has been done and validated with various universities looking at the advantages of hot over cold form. We at Tata actually do make both hot and cold tubes. Most of our cold form tubes is seen as commodity products which go into engineering or other construction applications. We don't put cold form tube into our prime building services applications because of the compliance issues and some of the issues which we've just talked about. We don't want tubes sort of splitting when they're being manipulated, and we do see a lot of manipulation in the market when building services with people either threading tubes, bending tubes, grooving tubes. So again, we tend to promote the sort of what we call the part 2 GH, the get hot, the normalized approach. When we come to talk about hot finished, again, you might be comparing a welded with seamless tube. Now, historically, seamless was always seen as the stronger, low risk option because in the very old days, and we're going back sort of decades, the quality of the weld was not as good. The steel refinement was not as good, but that's changed over the years. So now we would say that a hot finish welded tube through a reputable supply chain would be almost interchangeable with seamless in most of the applications we're talking about in building services. So whereas a welded tube is 10217, the seamless tube is 10216. So again, going back to that use of multi-standards to try and define what you're getting, it helps clearly define that, yep, it's a seamless tube. The problem with seamless tube is, again, when they get a billet of material heated up and extruded, there can be some inconsistencies on ovality and wall thickness. And again, seamless manufacturing process can vary. There's different processes which different providers of seamless tube might follow. So here's one example. And here's another example. They look very similar, but actually there's some differences in terms of how they process that tube once it's been initially extruded, stroke pierced. And again, seamless tube, because of the fact that it's being extruded, stroke pierced, one of the advantages it has is the microstructure is elongated as part of that drawing out process, which then means that tube is less likely to suffer from creep at higher temperatures compared to the coil-based manufacturing process. And the other thing is that obviously on coil base, we're restricted to about 16 millimeters. If the coil is any thicker than that, then we physically struggle to try and form that coil into a tube profile, whereas a seamless tube can extrude or be pierced with a very small ID, internal diameter element, which then means you can get a tube with big OD and very thick walls for very high pressure applications. As we've sort of mentioned, again, as a result of the manufacturing processes, we have this what we call end matching. So seamless tube, because of the way it's produced, the outer roundness, the inconsistencies, when it comes to welding those tubes together or jointing those tubes, you can end up with some misalignment issues. And when we talk a bit later about sort of corrosion issues and installation issues, it's worth noting that sometimes if you have seamless tube which has different end matchings, when they're welded together or joined together, there could actually be some steps internally, and that could act as an initiation point for corrosion or a place where debris can collect. So again, we will always try and promote the advantages of a welded tube because of that consistency and the tighter tolerances we were able to achieve. Then it means when you actually join tubes together, you don't end up with that change in geometry, which can cause some problems, which we'll talk about later. And again, this is just a summary of the interchangeability of a seamless tube with a welded tube. And I think the other thing we've noticed is that a lot of the reputable German seamless manufacturers are starting to sort of not do carbon steel. They're either pulling out completely or they're focusing on other higher grades of material, which gives them more value. So we do see a lot more seamless being imported from further afield, from outside of Europe. So it's always worth checking to make sure that product quality is there. But in most cases, in building services, a reputable seamless tube can be replaced with a Tata Steel welded product. And other than temperatures, being in excess of 400 degrees C, we would be fine for most of the applications. Same manufacturing process in terms of the testing, same as in terms of the CEB, the carbon equivalent value. They have the same steel grade, so they are interchangeable in most of those applications within building services where we're looking at maybe up to a maximum of 300 or 400 degrees C, and certainly pressures, temperatures. Again, we can go almost 50, 60, 70, 80, 90 bar, depending on the size of the tube and how it's being jointed, which we'll talk about later. When we talk about welded tubes, there's also what we call precision tubes. Now, a lot of people might be familiar with these thin wall press systems, press fitters it's called. We actually manufacture some tubing for this, and not in the UK, but in our Dutch mills. So we've got an understanding of thin wall, and thin wall precision tube has a number of advantages, but there are also some disadvantages which we'll talk about. But I wanted to make reference to this because, again, it's about the manufacturing processes, and the issue with this process route is that whilst you've got a continuous process and the tube is actually going through a galvanized bath, which is integrated in the flow line, so you end up with very thin wall, very sort of good cosmetic appearance tube. The tube is still a cold form tube, and obviously the issues associated with that is the heat effector zone is still present. And obviously, when you're deforming the tube or the fitting body, which can actually be made from a similar tube, then obviously you're adding additional work hardening there. The other thing to point out when we talk about jointing is obviously these press systems have an elastomer seal. So again, we've got examples of where the seal has been nicked or caught when it's been added to the end of the tube, which has caused leakages. When people are obviously using these tubes and being trained up and understand how best to use the tube, then they'll perform really well. But unfortunately, we've had some issues in the UK market where they haven't been really used correctly, and it's resulted in some rapid corrosion, which we'll talk about in a bit. Just referring to jointing, again, it surprises me when we talk to people about jointing, but people don't really understand the effects which jointing has on pressure integrity of the system. We'll get asked time and time again, what's the pressure rating of your pipework? And it's like, that's great, pipework can do up to 100 bar, depending on what grade of steel and what wall thickness you want. However, it's all irrelevant. The weakest link is the joint. So unless you're welding the tubes directly together, you're going to see exactly the same sort of pressure integrity. As soon as you start dropping down to flange joints, then again, good level of integrity, but it starts to fall off, and you can see as you get further and further to the bottom, then you'll end up with pressure decrease in terms of its suitability to take both application operating pressures and of course test pressures. So again, when people are looking at pipe work and doing calculations on service life and pressure integrity, that's great, but you have to bear in mind that the jointing is going to be the weakest link, and that needs to be taken into consideration as well. So just a quick case study about thin wall, and this is really to highlight some of the issues we have when you don't install pipework correctly. So say we manufacture a lot of this thin wall product, it gets used in Germany, for example, with no issues whatsoever. In the UK, it had problems, mainly because it's meant to be for closed systems, no oxygen, but of course we were seeing it being used in systems with oxygen, and also we were seeing it being used in systems where there was other materials, so dissimilar materials, other metals being used, and we talk about galvanic corrosion a little bit later on. But the problem which we have here is, again, pipework which has been installed incorrectly, not maintained correctly, not understood how some of these sort of application conditions can impact it. And what we saw is pinhole corrosion taking place as a result of galvanic corrosion reactions, and that caused a thinning of the wall in a localized area. And because this is thin wall material anyway, then obviously it corroded and burst quite quickly compared to traditional tubes. But again, this was all down to very localized corrosion, which was as a result of issues which could have easily been mitigated. But again, it was just highlighting the fact, again, it's so important about this heat effector zone and understanding what product you've got, making sure you specify correctly, because that HAZ, if it is present, is going to be an area of weakness. And it's also more prone to corrosion. We did a lot of work with Cranfield University and their corrosion science team, looking at the sort of potential differences across the tubes, and obviously at that sort of weld seam area. When you've got a cold form tube, you've still got obviously that stress in place which initiates corrosion. You've also, depending on whether the trimming of the internal weld bead has taken place or not, you've got the risk of crevices which can result in crevice corrosion. And then say with a hot finish process route, you're removing that risk because you're removing that heat affected zone by allowing that extra heat to be applied, which allows the grain structure to basically reorganize itself. So lots of the discoloration as a result of what we call the dislocations of grain structure, the change in the mechanical properties local to that grain structure. Of course, the heat treatment process allows that to reset itself and again give you a much better product technically. So when we talk about sort of pipe work and the specifications, I think it's important to identify exactly where the pipe work is being used and some of the issues which then obviously need to be taken into consideration. So we're talking about obviously corrosion. Carbon steel does corrode. However, carbon steel can be exposed to a variety of different application environments, and as long as it's understood what those application environments are, then the risks can be easily mitigated. But what I'm going to do is just go through the various different corrosion mechanisms. And again, whilst inhibitors can be used as a means of mitigating the risk of corrosion, again, we'll touch on the fact that certainly from some of the evidence we've seen that correct use of inhibitor or making sure that the inhibitor is in the right quantity and it's circulated right through the system can be a bit of a challenge, which can give people the false sense of security. We've dosed the system, we've got an inhibitor in, so it must be okay. But if that inhibitor is the wrong inhibitor, the wrong strength, or not getting around the system, then actually you can have other issues which are going to cause corrosion. And corrosion is pretty well understood. It's one of the biggest reasons for pipework failure based on the data which we've got. However, we do know the reasons behind corrosion, open systems, closed systems. An open system is going to have more oxygen in. However, closed systems, again, can also have the same amount of oxygen in, particularly if they're leaking or somebody hasn't actually made sure that system is leak tight. So again, understanding that what we call the electrochemical reaction, where oxygen plays a key element to that. But also we can see corrosion initiate as a result of geometry. It can be down to galvanic reactions, which we'll talk about. And again, when we've got debris within the system, either part of the commissioning process or as a result of corrosion taking place elsewhere as a result of galvanic corrosion, then that can obviously result in a different type of corrosion itself. Now, I don't want to basically say carbon steel is going to be, always at risk of corrosion, because obviously correctly installed and maintained carbon steel tube can last many, many decades. And again, most people tend to allow for some sort of corrosion allowance when they're doing their design. And what we're sort of saying is actually we can work more closely with you to look at the application and look at how the pipe work is being installed, look at the grades of steel. Those higher grades of steel will allow you to go to thinner walls, have an initial resistance to the onset of corrosion. So as we try to look at being more responsible with the amount of steel we use, B, looking at weight savings, which obviously then result in what we call embodied carbon savings as well. So carbon steel has many decades of use in building services without issue. However, we are aware that when there are issues, normally it's not so much down to the tube, it's down to something which has happened in that installation or something which has not been done or an assumption which has been made which has been incorrect. And again, when we look at the sort of types of corrosion failures, uniform corrosion is only about 30%. Localized corrosion is really where the main issues occur. And again, when we talk about uniform corrosion, normally within a pipework system, you'd expect to see some form of uniform corrosion take place initially. But once the oxygen is depleted, that system stabilizes and then it will just sit there nicely. Most of the concerns or issues we tend to see now, again, are normally to do with corrosion on the outside of the tube. And that's taking place in the uniform manner because any sort of installation which has been put around the tube has got wet or damp or there's moisture in there. And that means that you've got water and oxygen sitting on top of the tube, which obviously can sort of break through any protective coating and cause corrosion. And again, going back to the cold form tube, that heat affected zone obviously is inside the weld seam. It's both on the top and the bottom. So again, if you've got a tube which is completely covered in water as a result of saturated installation, then that weld seam is going to be prone to accelerated corrosion as a result of the heat affected zone and the stresses associated with it. The localized corrosion can take place due to a number of different mechanisms, which we'll talk about now in a little bit more detail. So at the start of the presentation, I made reference to what was called galvanic corrosion. Now, galvanic corrosion has become more and more of a problem as far as I'm concerned in building services. And this is because historically we used to see a lot of people use traditional thick wall tube. When thin wall precision tube came into the market, it came across as being a much simpler, easier to use product. Certainly its speed of jointing installation was a lot faster, so speed of work, time savings. Lightweight tubes are easier to carry around, and it was sort of presented as a, dare I say, a low skill installation, because you could just crimp the joints. You didn't have to basically look at roll grooving or the skill of threading and making up a leak tight screw to socketed joint. The problem was, as we talked about in some of the earlier slides, corrosion became a big issue and these tubes started to fail very quickly, and it was more to do with the commissioning, which we'll talk about in a bit. But we saw a lot of people switch across to stainless steel with the belief that stainless steel didn't corrode and they could have these thin wall tubes. The problem is that stainless steel does corrode, but more importantly, it's more cathodic in what we call the galvanic series. So stainless steel can be used in like process pipe work, catering pipe work, but the rest of the system is also stainless steel. When you see stainless steel being used in building services, normally there's other materials such as carbon steel or copper in those pipework systems. So we call them mixed metal hybrid systems. And what you have now is a range of different materials sitting at different positions across the sort of galvanic series. So when a product is more the cathodic area, it's more resistant. As soon as it starts to move or the material is more anodic, then that material will corrode faster or sacrifice itself as a result of the electrochemical reaction. So when you start seeing stainless steel being added into these mixed metal hybrid systems, it then starts to cause everything else below it in the series to accelerate faster. And this is where we start to see a lot of issues. The issue also relates to mixing different grades of stainless steel, because they in themselves have their own little bit of galvanic series as well. So again, you can see from this chart here that as you move away from the more sort of stable materials, such as platinum, moving all the way up through lead, tin, iron, zinc, aluminium, you start basically seeing these different rates of reactivity. And on the graph, which hopefully you can just make out, you can sort of see stainless steel grades exist at a variety of different locations. And, this is galvanic series has been something which we've been used to for many years, because carbon steel tube is actually protected by zinc when we do the galvanizing process. The zinc sits more towards the anodic range of the series, so it's going to sacrifice itself to protect the steel, which is not necessarily a bad thing, because the zinc corrodes at a much slower rate. The zinc oxide which is produced is not as harmful to an installation as the iron oxide from rust. So the zinc sacrifices itself to protect the carbon steel. And then if there's stainless in the system, the stainless steel basically protects itself by having everything else below it sort of accelerate in terms of corrosion. So when we talk about mitigation of this, it's about making sure you select materials which are close in that galvanic series, or avoid having such a big wide range between this sort of anode and the cathode, to try and sort of, again, control that electrochemical reaction. So I think galvanic corrosion has become more and more of an issue over the years as we've seen different materials being used in pipework systems. We've seen some people revert back to traditional. We've seen other people look at other technologies, other materials, moving towards plastics or alternatives to try and basically have something which is, again, sort of easy to install, but we're sort of seeing, again, a lot of issues where people aren't then taking into consideration these main considerations as we've listed. So again, the temperature of the system, the pressure, the concentration of what's in that system, the pH, the dissolved oxygen, etc., etc., etc. So there's a lot of science behind this, but again, just questioning your materials which are being used in your pipework and where they sit on that sort of galvanic series is a good starting point to try and understand whether you're going to have a bigger problem or not. Other types of corrosion which initiate, we call crevice corrosion. Now, crevice corrosion is normally associated when you've got two different components sort of next to each other, either a flange plate or a bracket or something like that. However, crevice corrosion also occurs within pipework systems, particularly if the internal well bead has not been trimmed properly. You end up with a sort of internal lip where the oxygen at that point is depleted, so it's more prone to corrosion. And again, there's issues which we're aware of, and again, mitigation which can be put in place. And we'll talk about the sort of crevice corrosion again a little bit later on in one of the examples we show. Pitting, so going back to the thin wall tube, pitting occurred because we saw rapid acceleration in a very localized place. So again, pitting is normally as a result of something which has either happened on the surface of the tube. Either there's a defect there or there's a localized breakdown. It could be that pitting takes place because of another corrosion reaction called MIC, microbiologically induced corrosion, where debris or biofilms build up on the internal surface of the tube. And you can see from the diagrams here that lots of different pitting mechanisms which take place. And again, this goes back to the steel chemistry and the grade of steel which has been specified. But again, there's lots of things which can be done to mitigate the risk of pitting corrosion taking place. And whilst this is not an electrochemical reaction, erosion is something, again, which we're starting to see more and more of an issue of. And this comes about because obviously if we've got like a mixed metal system and we've got corrosion taking place elsewhere as a result of the galvanic series, then that corrosion inside the tube can result in debris. That debris can obviously then go around with the flow of water within that tube. And of course, when you've got sort of changes in geometry or as we can see here, a bend where the turbulence may be almost shot blasting that debris into the side of the wall, you can see we end up with a thinning of that wall, which then becomes again an area of weakness, and the sort of a pitting takes place. And then depending on your pressure, you can end up with that wall breaking through. So erosion is something which we are more aware of as a result of galvanic series and debris within the systems. Obviously strainers and other means of collecting that debris or preventing the risk of that debris again, but when they're also corroding as a result of the galvanic series, then obviously you can end up with systems which are heavily contaminated. I mentioned MIC, so again, we saw this as part of an issue, particularly with what we call sprinkler tubes fire defense, where as part of the commissioning process or charging process, tubes will be filled with water and then they'll be drained down. In building services, it might be they've drained down because the building had been commissioned, but no one's going to be in that building straight away, so they drain it down ready for the new owners to move in. Or for sprinkler systems, it could be a dry sprinkler system, so they do an initial wet load test. Once everything's all checked out, the system is drained down, ready for it to be initiated once a sprinkler head is activated in the case of a fire. As a result of that drain down process, water was being left behind. And again, where you've got sort of dead legs or changes in geometry, places where water can collect, after a period of time, that water can become stagnant and it can break down, particularly if there's bacteria in the water or the water is poor quality. These produce these biofilms, and underneath these biofilms, we can end up with pinhole corrosion, which can take place quite quickly. And again, going back to the case study on the thin wall tube, we started to see this happen quite a lot when they were first being installed. Pipework was being commissioned, it was being basically water tested, and then they were being drained down. It was leaving water behind, which was then breaking down to produce these biofilms. Those biofilms were then not becoming stable. They were basically active, and because of the thin wall, they were obviously resulting in the very localized pinhole corrosion. So again, understanding what's in your system, understanding that if you are doing flushing, then obviously there's certain things which can be added to try and reduce the risk of biofilms taking place. And again, commissioning can be a CPD in its own right, quite a complicated, complex subject. However, we know that most of the processes involve some sort of flushing out of the debris, which is good because debris, as we've seen, can cause corrosion mechanisms. The chemical treatment of the internal surfaces as part of a cleaning process can be quite beneficial in terms of removing any sort of debris or internal scale which can contribute. However, with thin wall tubes, they're actually supplied with an internal protective coating, and the problem is that the chemical treatment which was taking place to clean the tubes was actually stripping off that coating. So again, leaving the sort of exposed virgin metalwork open to the elements, and then obviously that was again initiating corrosion. So again, making sure that if you are flushing and leaving systems, that the biocides and inhibitors are used. And again, we have a variety of different resources which we follow, but again, I've put it at the bottom here, the BSRI guides tend to be what the industry refers to. And we're talking about commissioning and cleaning processes using sort of chemicals, but we now know that there's remote monitoring, which again allows people to monitor systems. And again, again, there's a big debate going on at the moment about what's the best way of commissioning, whether it is with chemicals or whether it's with remote monitoring. We quite both, because obviously the commissioning with chemicals means that you're cleaning the inside of the tube. You're obviously, if you're using biocide washes or inhibitors within there, you're going to be adding chemicals which are going to mitigate the risk of bacteria, which can result in corrosion. However, if you've got real-time monitoring, you're collecting data which allows you to start to ascertain whether something has changed in your system, and it might not be down to pipe work, it could be down to something else which has either failed or some other retrofit work which has taken place, which has added more oxygen into the system. So a mixture of both might be quite beneficial. I was going to talk about some additional product testing which we undertake. However, I'm conscious that Tata Steel has been in news quite a lot about its sort of sustainability journey. The UK government has made an announcement that it's going to invest heavily in Port Talbot in terms of changing the sort of nature of our steel make. So as a result of that, I just thought I'd cover that in a couple of slides just to bring you all up to speed on what's really happening. And again, pipe work going forward, we do see a huge opportunity to make sure that people are on the right grades of steel. Stronger grades of steel allow us to have thinner walls, but thinner walls, again, as long as we understand the application, we can control and mitigate the risk. And it might be strange to hear a steel manufacturer saying we don't want to sell as much steel, but we want to be more responsible with the steel. And certainly with regards to the sustainable focus, we can take up to 90% of embodied CO2 out by using a scheme we've got called Optimus, which we'll describe a little bit more. But more importantly, we can take weight out and therefore embodied carbon out by result of being smarter about the design of the pipework or how it's used. So again, higher grades of steel allow for wall reducement, which again brings commercial and other application benefits. But the big announcement which we had recently, again, which has been in the news, is this £1.25 billion investment around the steel make. So at the moment, I mentioned that we get all our steel from Port Talbot. Port Talbot has blast furnaces. Those blast furnaces are a big emitter of CO2. So we're trying to basically look at how we can be more responsible to reduce that CO2. We're already a responsible manufacturer. We responsibly source all our raw materials to make our steel. And again, going back to that earlier slide, which showed the standards and the steel chemistries, that's why it's important to specify, because we obviously have to change the ingredients to get those mechanical properties, and different products have different mechanical properties and different benefits as a result of those properties. But the steel making process is basically allowing us to melt these raw materials down and then obviously produce the molten steel, which goes into slab and slab processed into coil. We've had a strategy. Basically, we've reviewed multiple strategies, and really we've been waiting for the UK government to confirm its industrial strategy and its energy strategy. Really, because we were at a bit of a crossroads in which direction to go. And there's still some debate, but at the moment, the decision or the initial investment, which we've been given by the government and also being matched by Tata Steel. So I think it's 500 million from the government and 750 million from Tata Steel to look at moving away from blast furnace to electric arc. Now, the decision we had to make, or obviously the crossroads we were at, was do we keep blast furnaces and move them over to hydrogen, which is more environmentally friendly? The problem is that hydrogen powered blast furnaces is relatively niche, and again, hydrogen, whilst more environmentally friendly, has to be produced, and that requires an awful amount of electricity. So we looked at the global sort of supply chain and looked at what other people are doing, and really electric arc is seen as the better bet to reduce the amount of CO2 we generate, and it's also a proven technology, and we've already had the number of electric arcs in the UK, and globally a lot of this sort of steel producers have electric arc. So the decision was made to look at going down the electric arc route rather than the sort of hydrogen blast furnace route. And the advantages of that is that obviously at the moment when we're making virgin steel, we can maybe use about 17% recycled. steel content. Now that might not seem like a lot, but we're starting that steel journey. We're making the virgin steel. If we put more in, then we start to influence the mechanical properties because we're making it from the raw materials. However, electric arc allows us to utilize existing scrap. Now there's an awful lot of scrap in the UK. Most of it gets exported. The idea is that we'd be looking at utilizing that scrap and segregating it into the right grades of material, which we need to then basically melt down as part of this electric arc process, and then refine that steel to basically produce the slab and then back into the coil. And the beauty about obviously the electric arc is all the energy which is used to melt that down, the electricity which is used can be provided by renewables. So as well as obviously looking at what we can do in terms of the steel make, we're also looking at what happens in terms of Wales and its wind farms, solar farms, which can then be used to complement what we're doing, as well as looking at a recycled industry in the UK, a green recycled industry, which is segregating that material so it's used locally within the UK rather than being exported. And again, the advantage of what we're doing here in terms of the sort of electric arc process means that any material, when it comes to the end of its usefulness, basically we can look at options of taking it back or putting it into that recycle process to basically turn back into tubular products again. So the move to electric arc is probably going to take between 3 to 4 years, and whilst that's happening, we're obviously looking at other activities to lower our CO2. So across all our business, being the upstream steel make or the downstream tube manufacturing, for example, we've all got lots of different programs and exercises in place where we're being a lot smarter about how we basically utilize our resource and also what we can do to reduce our CO2. The biggest impact is obviously going to be the steel make, but downstream businesses, and for example, I'm based at Corby. We have our tubes mill there. We're going through a site reconfiguration where basically we're cutting our site in half. We're pulling away from old warehouses which are inefficient in terms of trying to heat them, lighting for them, lots of energy being wasted. We're moving away from 2 mills which were older mills and putting in a new brand new combination mill in to allow us to have better efficient mill technology. As a result of the smaller footprint, we're not losing capacity but being a lot smarter about the site logistics. So everything's going to be in one building instead of multiple buildings across the site, so we're not moving things around by trailers. And we're moving away from gas heating as part of that heat treatment process to induction, and of course we're then looking at renewables for that energy. And little things like screwed and socketed, supplying a tube with no sockets on the end so people can use the right fittings. We see sockets being used as either thread protectors or some people think that they're not suitable for particular applications, so they tend to get discarded. So again, that has a small but again contributes to an overall reduction of our CO2. So whereas offsetting is seen as planting some trees and being seen to be green, we're actually doing insetting. So we're physically changing our manufacturing processes to get that CO2 emissions out. And whilst we're waiting for the electric arcs to sort of kick in fully, we've got Optimus, which is bridging the gap. And Optimus works in a way that we've had DNB, who's a third-party independent auditors, come in and looked at our manufacturing processes and identified the amount of carbon which we have as a starting point. We are then obviously reducing the embodied carbon as a result of our process improvements and some of the investments which we made reference to. That reduction in carbon is being converted into carbon credits, which are then certified. And rather than us saying that we've got a small percentage reduction in embodied CO2 across our products, we're focusing on key products such as our building services tube and applying all those carbon credits, which allows us then to basically reduce the embodied carbon by up to 90%. So we can see from this table here that if we start looking at the weight of a medium tube or to a heavy wall tube, then obviously having a higher grade of steel, such as the 235 grade compared to the standard, which asks for a 195, means that you can go to a thinner wall, still get your pressure integrity, but you've got a weight saving, which is a CO2 saving as well. However, applying the Optimus on top of that, we can bring it down by up to 90%. And when I gave the first CPD, we had a rough example, but since we did this, we've now had a project in London, which is basically taking the Optimus tube. So we worked with the specifiers and the consultants, and we were able to convert the initial large diameter pipework from imported shed 40 seamless to UK welded shed 20. The higher grade of steel meant that we can satisfy the service life and the pressure integrity. So that technical conversion saved 180 tons of CO2. We then applied the Optimus on top of the existing pipework, and that gave us a total saving of over 500 tons of CO2. And that's now a project which is in London, which is now looking at applying the same on other floors. So actually the CO2 saving is going to be even bigger. And when you start getting into the statistics about the CO2, again, you see how much 1 ton of CO2 is equal to, then you can see that this is actually something which I think building services can really bring to the party. You know, the end client wasn't aware that he could achieve so much CO2 reduction through the pipe work within the building services. It allowed them to basically demonstrate a reduction in the embodied carbon, which supported other activities he was doing to try and get the CO2 out. Going in and looking at the existing pipework systems, allowing us to basically make recommendations for how it can be changed, optimized, sizing of tube, is all something which we can provide as Tata Steel. We had an example, another project in London where the riser is basically being replaced due to previous corrosion issues. It was a non-Tata Steel product. However, it was 600 nominal bore. We've made recommendations to move to 500 nominal bore to bring it into Tata product. And more importantly, with the grades of steel and the wall thicknesses we can achieve, there's a huge commercial stroke weight saving. So there's already a big CO2 reduction on that job being proposed. And then also with the Optimus being applied, we can take those CO2 savings even further. So we're starting to see some of the big nationals really ask for CO2 reduction strategies, and we're in a good position now to be able to deliver that. In fact, when we look at our core elements in terms of who we are and what we offer, product guarantees, the compliance has always been a key area of focus, the technical resource, which we can give either with the technical team which we have, or the work which we do to support the industry with the various collaborations we've got with the trade associations or universities. But sustainability is now there as the key factor which we're all focusing on in terms of everything through our supply chain, from the steel make to what we do at tubes, and certainly where the building services products can benefit. And like I say, we're here really to work more closely with the market to try and basically look at the opportunities, because I think if we can get the right product into the right application, then obviously that product can last for many years. And again, there's a huge benefit in the amount of CO2 we can take out. So conscious we've talked quite a lot, and again, the objectives for today were really to go into a little bit more detail compared to the basic CPD. Certainly talked about corrosion a lot, and again, that's really to try and demonstrate we understand a lot of the mechanisms, and actually with stronger grades of steel, you can go to thinner walls. Some concern about thinner walls as a result of previous legacy issues on what we call press fit systems, but again, a lot of those applications, the tube was being installed without really understanding what conditions it was being exposed to, and obviously people not really understanding the differences between cold and hot and how that can impact on the performance of the tube. So going back to the manufacturing and the standards and the specifications being correct is key, and hopefully that's something which we can carry on working with the industry and CIBSE to improve the awareness to make sure that the right specs are in place. Thank you for your time.
Excellent. That's great. Thank you very much, Chris. Really interesting and informative. Thank you very much for that. I especially like the section about inhibitor being both good and potentially bad addition to the system. As you said, if it's there, it can give a false sense of security, and if it's not getting around the system, then it's not being effective. And yeah, really interesting. And probably that corrosion piece would be a subject in its own right. So thank you for that. Just while everybody's gathering their thoughts, just a plug, if I may, before we get into anybody else's questions. So tomorrow we've got a Society of Public Health Engineers Insights into Sustainable Innovation with the PAM Building webinar seminar. And then on Thursday in Birmingham City Centre around lunchtime at Jacobs offices, there's a hydrogen, the future of heating in the decarbonised gas grid event on as well. And then next week not next week, maybe the week after, because of the half term, on the 7th of November, we've got a barrier pipe for potable water supply in contaminated land event. and then on the 14th, a reflection on the regulation as a way of working for the building regulations approved document Part O overheating event, followed on the 16th November with a water treatment masterclass for our young engineers. You can sign up to attend and benefit via our Eventbrite page. Details are in the chat, and you can catch up with any of our previous events that were videoed by subscribing to our YouTube channel and watching and catching up there. Any feedback, thoughts and comments would be welcome by emailing feedback@cibsewm.org. I'd like to take the opportunity to thank everybody who's joined us for doing so this evening. It's great to have you with us. Thank you very much. And also to thank Chris and the team behind the scenes too that have made today's event possible. Thank you all very much as well. I look forward to meeting and welcoming you to a CIBSE West Midlands region event in the near future, and I wish you all well for the rest of your day.
Okay, thank you very much for your time, and look forward to working closely with CIBSE going forward. So thank you very much.